Hello, everyone. Welcome to today's Venting Strategies online seminar. My name is Miranda Gentling, and I'm the Academy Manager here at Viessmann US. And I just wanted to say thank you for attending today and welcome. Today marks the last PDH accredited presentation we will have in 2020. And I wanted to also take this time to introduce you to your instructor. For those that may not know him, is Jody Samuel. Jody is a graduate of Maine Maritime and Academy with a degree in marine engineering. Over the past 20 plus years, he has worked with various companies, including Amtrol, Viessmann, and Colefi, serving in various roles, including application engineer, product manager, training manager, and manager for engineering education. Currently, he serves as project development manager for Viessmann. And before Jody begins, I do have a few housekeeping items to go over with everyone. And the first is as I stated, this is a PDH credited presentation, and RCEP is the provider we do this through. And they do have a requirement for a survey to be filled out by anyone who would like this credit. And you will receive that survey via email by the end of the day today. And once you fill out that survey, certificates will be emailed out to you in about 5 to 7 business days. And if you aren't sure if you clicked yes on the registration form for receiving this credit, the Academy email will be on the last slide today, so feel free to email us and we will double check for you. Again, everyone will stay muted throughout the entire seminar. However, at the bottom of your screen, we do have that Q&A button. You can click on this Q&A button and type any questions you have in throughout the entire seminar. Jody will stop about halfway and at the end of the presentation to answer any questions submitted. And we will be putting together a spreadsheet of all of the questions asked, and then Jody will fill in all the answers, which we will send out to everyone in attendance today. We are recording today's seminar, and it will be posted in our video library on our Academy website, Viessmann-usacademy.com, same website you went to register for this seminar. And there's two ways to get to that video library. The first place is up top in the header, or if you scroll down, we do have that larger video library section that you can click into. And once you're in that video library, this is what you will see. And up top, we do have that search function, so you can simply type in venting strategies, and this video will populate. Or we have that recorded online seminar section down below, where this video will also be located. We will be posting this on our YouTube channel as well. So if you go to youtube.com, Viessmann North America is our page, and look at the videos, you can find this one and all of the other videos as well that we have. And with that being said, let's begin. Here is Jody Samuel.
Thank you, Miranda. So today we're going to talk about venting strategies. Miranda did a great intro. Couple of slides before we get into it. I'm not going to talk about this. Miranda talked about the certification. The presentation is copyrighted. So if you would like a copy of it, we can provide you with one. Just when you get the survey, fill the survey out and make a note in there, like a copy of the presentation, and Miranda can get you a PDF version of it. I'm going to skip through the statement of purpose and kind of jump down to the learning objectives. So upon completion of this webinar, these are really the things that we're discussing you should have some knowledge about when we finish. So we'll talk about the factors involved in vent sizing. We'll talk about equivalent lengths, how they're calculated for venting, and that comes into a lot of applications. We'll talk about the difference between category 1 and category 4 venting. We'll describe the sizing process for venting. And finally, we're also going to talk about what's called the Jakowski Effect as it applies to boiler venting. And this is starting to get more and more into our conversation. Now, for me, this is, like a lot of the presentations I've done, this is a topic that day in and day out, week in, week out at work, this is part of what a lot of my conversations revolve around with reps and engineers and other people using our product. I probably talk about venting on average at least once a week. Now, from a venting standpoint, there's not one single location to get your information from. The one thing about the reference of this, a lot of times when a question comes up, I have to look at different sources. So first off, you have a few NFPAs listed there, NFPA 54, 31, and 212. So 54 deals with gas-fired equipment. 31, information on underwater oil-fired equipment. Nfpa 211, it has general information about venting. So when somebody has asked questions about a project, a lot of times they may reference one or two of those different manuals. In addition, every manufacturer will have manuals on venting to reference as well. And then finally, the other place that a lot of times I end up referencing is venting manufacturers. Here I say sizing software, I have that on my computer, but a lot of times I'll go to some of the vent manufacturers to pull up information as well. So there's a lot of information out there. It's just about gathering it up and picking up the right pieces of information. Okay. Now, for our discussion, we're going to talk about a wide variety of venting. Here's a couple of pictures of venting from the equipment that heats our building in Rhode Island. You know, when I'm doing venting systems, it may be a category 1, could be category 4, or could even be category 2 and 3. Now, one of the key points I do want to point out when we start to talk about venting, boiler venting is going to be certified venting systems. So they are venting systems and they're certified. You know, over here, this is category 1. This happens to be a cast iron oil, a dual fuel boiler. And category 1, you'll see my barometric here, which means to me, this vent is going to be under a negative pressure. Over here, this happens to be category 4. In category 4, there is no barometric. This is under a positive pressure. The other big key between the two is these boilers are both the same firing rate. You know, category 4 typically runs smaller than the category 1 venting systems, and it's really about the mechanism that allows the gas to exhaust out of the boiler and outside the building. Now, one other thing about this, and this has come up in conversation, that's why I want to mention it, these are certified venting systems. So just because one of the materials used in a category 4 vent may be AL29 4C special stainless, just because you have a source of stainless, you cannot build your own category 4 venting. Yes, it has been done, and you know it was not something that was certified or actually long-term use in the system because of that. So they are certified venting systems. Okay. So from an aspect of venting, typically everybody thinks about the categories here. These categories 1, 2, 3, and 4. From an aspect of the rating, it's really about the vent pressure. Is it non-positive or is it positive? Is it going to be condensing or non-condensing? So for instance, if I'm doing a cast iron gas-fired boiler, it's probably going to be category 1. It's going to be a non-positive, non-condensing application. Conversely, if I'm doing a condensing boiler, it's going to be a category 4. It's going to be positive pressure in the venting, and it's also going to be condensing, both condensing in the boiler and in the chimney itself, the vent itself. This is also why your vents have different materials depending on what the venting has to deal with. Now, one other that I run across every once in a while, particularly because we sell cast iron boilers that can either be fired with natural gas, propane, or oil. These are gas appliance vent categories. Every once in a while, somebody will call up and say, hey, can you size for me or help me design a category 3 vent for an oil-fired boiler? And my answer always is no. Oil is not considered to be category 3 type application. Category 3 is a gas appliance. For most of our discussion, we will primarily focus on category 1 and category 4 as well. Now, when we start to look at sizing and the information, a lot of guys will come up, will send me an email saying, hey, I'd like you to take a look at our venting system and see what you think of it. There's a lot of information that goes into whether that vent system will work or that won't work. And it's all about moving the combustion gases. Here, this happens to be a category 4 venting. Why? Well, I notice there is no barometric in here. So it's all about moving the combustion gases out of the boiler and out of the building to someplace where they safely can be exhausted. You know, same thing over here. You notice here's my barometric. This actually happens to be an oil-fired boiler. But again, it's all about sizing it properly that I can move the gases out of the boiler and then out of the building where I can exhaust them safely. And to do this properly, there's a lot of things that have to be considered. So we'll work our way through these, starting with the mechanisms that actually move the combustion gases. Now, the first of these mechanisms is the draft, the natural draft. And a lot of people talk about the available draft for an application. And where this draft comes from is its draft is associated with a vertical chimney. And the draft is what actually moves the combustion gases through that chimney. And how that draft is generated is basically the combustion gas temperature is higher than the ambient temperature outside. And because of that difference in density, that causes the gases in the flue to want to move up and out of the building. Now, when we look at how that flue gas moves, or the mechanism that moves it, and the amount of pressure it can provide to move that gas, there's a couple of things that we have to consider. We have to consider temperatures, and we have to consider stack heights. Let's first start off talking about the temperatures, the air temperature and the flue gas temperature. So as I said in the previous slide, this draft is generated because the flue gas temperature is higher than the ambient temperature. And because that flue gas is hotter, the gases are going to be less dense, and that lower density is going to provide the mechanism that moves the combustion gases out of the boiler and up through that chimney. Now, how much is being generated? There's a bunch of factors involved in it. The first factor really is the differential temperature between the two, okay? In general terms, the bigger the temperature difference, the more pressure we'll have available to move it. So for our discussion about available draft, we're first going to say, okay, well, let's take a look at it. And let's say this stack height from here to here is 30 feet. And when we talk about draft, we're not talking about a whole lot of pressure. Typically, when we deal with moving combustion gases, normally it's in inches of water column, in fractions of inches of water column. So if I have a 30-foot chimney or 30-foot stack, and the combustion gases are 300 degrees, and the ambient temperature is 60 degrees, that 30-foot chimney is going to generate about a negative 0.14 inches water column of draft. So that negative 0.14 inches water column is what's available to move the combustion gases up through the vent or the chimney and out of the building. Notice if I drop my outside temperature from 60 degrees down to 0, and I keep it at 300, that negative 0.14 inches becomes a negative 2.0 inches of water column. So again, the bigger the temperature difference, the higher the draft becomes, the more flow resistance the chimney can overcome as well, okay? It will also go up as I raise the flue gas temperature. Again, it's all about the temperature difference. So if I bring that flue gas temperature up to 400 degrees and leave the ambient temperature at 60 degrees, I'm going to generate a negative 0.17 inches water column. So when we start to look at a chimney being effective, one of the things we have to know is what's going to be the flue gas temperature and what's going to be the ambient temperature. Because a chimney in the middle of winter in Bangor, Maine, is going to draft a lot differently than a chimney of the same size, say in Los Angeles, California. So we have to know about that when we're actually designing the system. It's about temperatures for the draft. Now, the other thing that comes into play is the stack height or the vent height. Simply stated, the taller the chimney, the more draft you have, because you're generating a taller column of warm flue gases. So if I say that, for the sake of this discussion, let's say I'm just going to stick with that 300 degree flue gas, and let's leave the ambient temperature at 60 degrees Fahrenheit. If that chimney is 30 feet tall, and these are numbers we talked about in the previous slide, I'm going to generate a draft of about a negative 0.14 inches of water column. So that's the amount of essentially pressure that's available to overcome the friction through that chimney. Now notice if I cut that chimney in half from 30 feet down to 15 feet, now I'm dropping down to a negative 0.07. Half of the chimney, half of the draft. So when we start to look at what size chimney I need for an application, I really need to know how tall the chimney is, because as you see here, if I'm thinking I have a 30-foot chimney and I only have a 15-foot chimney, I only have half of the draft to work with when I'm trying to design it for that application. So from a natural standpoint, for a chimney that has a vertical component to it, a vertical chimney or vertical venting, I can generate draft, but I need to know temperatures and I need to know heights. Now, a lot of times when we think about category 4 appliances, we think about positive pressure in the venting and the boiler essentially providing the pressure to move the combustion gases through the chimney. However, if I'm doing a condensing boiler, because the flue gas is at a higher temperature than the ambient, a vertical chimney on a condensing boiler will also generate draft. It's just with that condensing boiler, I typically deal with much lower flue gas temperatures. So let's say I have a 15-foot tall stack attached to a condensing boiler. The flue gas is 167 degrees Fahrenheit. The ambient temperature is 60 degrees Fahrenheit. The developed draft is a negative 0.04 inches of water column. Okay? So at that temperature, the draft is about half the draft that I would have saw at 300 degrees Fahrenheit, a little bit more than half. But the thing is, when I do a condensing boiler, because of that flue gas temperature, there's still a draft that does occur. If I bring that chimney up to 30 feet tall, the draft goes up to a negative 0.11 inches of water column. And, even down at a flue gas temperature of 130 degrees, I still see a draft as well. So when we start to look at designing condensing boilers, one of the things that from a standpoint of vent size, venting design, if the venting is vertical, there still is an available draft that I can utilize in that sizing procedure. Now, when I'm doing category 4, category 4, all of a sudden I start to bring into other things besides a vertical vent. Horizontal now comes into the picture, because here we're talking about a positive pressure. So when I do category 4 venting, not only is there draft available if it's vertical, but there's also positive pressure. And that positive pressure comes from the burner assembly. So whenever you look at a category, a condensing boiler that's going to be vented category 4, somewhere in the manual, they will give you the positive pressure expressed in inches of water column. Is it 0.4 inches? Is it 2.8 inches? Is it 0.6 inches? This is boiler specific for that boiler burner combination. But this positive pressure is what's going to overcome the resistance up to the flow of the venting system. So that's basically the amount of pressure you have available to overcome the friction loss in your vent system. Okay. Now, a lot of times when you look at these numbers, you will see a wide variety of positive pressures that are available. Okay. The one thing to consider is a lot of times somebody will say, this boiler here, I like this boiler because of the fact that, it can generate high positive pressure, which allows me to either go really long on the venting or go small on that venting size. The thing is, in order to generate a large positive pressure, normally what we're looking at is an application with a much larger blower with a bigger electric motor and also a larger electrical draw. In some cases, if the positive pressure available is on the lower side, I may be looking at a boiler that's taking 120 volt single phase. Whereas, in order to generate some of these positive pressures to get the vent size down, all of a sudden you may be going to a much larger single phase motor or even into a 3-phase motor to get to that smaller vent diameter. So when we look at the available positive pressure, there are some pluses and minuses when you start to look at what's available there for these positive pressures. Excuse me. Okay. Now, I have to throw this in here. You know, it's kind of hopefully one of the obvious things, but it does come into the discussion. And a lot of times this comes into discussion because of this right here, because of how somebody sized the boiler in the vent system. The thing is, one of the things that has to be considered with the venting system is the boiler firing rate, because the higher the firing rate, the more the amount of exhaust that comes out of it. So for instance, if I'm doing a 1,000,000 BTU boiler, and it's a gas-fired boiler and natural gas, and it's at 12% CO2, it's producing 12.82 pounds of combustion products. Okay. Now, if I increase the firing rate from 1 million to 1.2 million, the combustion products increase to 15.39 pounds per minute. So whenever we start to do the sizing, it's part of the sizing is I have to move that amount of combustion gas based on the firing rate through that venting system. So it's important that the firing rate of the boiler is known. It's also important if somebody makes a change in the size of the boiler, then the venting system has to be resized, because that vent system that's sized for 1,000,000 BTUs may not work properly at 1.2 million BTUs. Now here I'm talking about it in terms of pounds of flue products. If I look at it in terms of velocity, let's say somebody says I'm doing 1,000,000 BTUs and I want to use an 8-inch vent with that 1,000,000 BTU boiler. At 1,000,000 BTUs, the velocity in an 8-inch vent is going to be 709 feet per minute. If I increase the firing rate to 1.2 million, the velocity increases up to 850.8 feet per minute. So when we start to look at sizing, one of our goals when we start to look at sizing, it's all about friction in the vent system. The higher the velocity, the higher the amount of friction. So when we look at the firing rate of the boiler, we then have to look at the size of the venting to keep the velocity down to a reasonable range for that vent system sizing. Now, along with the firing rate of the boiler, we also have to know how much excess air is going to the combustion process, because I need a certain amount of air that's required to burn my fuel, but I'm always going to put in excess air, and the excess air is to make sure that my combustion process always burns clean. I don't want to make soot and I don't want to make carbon monoxide. So there's always an amount of excess air. But the excess air can change depending on conditions, but it also depending on how the burner is set up, or even the model of burner that's utilized for some of the we'll call them category 1 boilers. The thing with it is if I increase the excess air, the firing rate of the boiler is still the same, but now that the overall mass of gases, combustion gases that are exiting through the vent piping, the flue, has changed, I have to make sure I know about this to be able to make sure everything is sized properly. Because for instance, if I was doing a 1,000,000 BTU boiler and I had 9% CO2, which ties me to a certain amount of excess air, and I had an 8-inch vent, the amount of mass that's moving through there is 16.45 pounds. In an 8-inch vent, that equates to 909.9 feet per minute. If I don't do anything with the firing rate, but let's say I add more excess air, and my CO2 dropped from 9% down to 7%. So I've probably added maybe another 20-25% excess air. With that same 8-inch vent, that 16.45 pounds now becomes 20.6 pounds. The velocity of 910 feet per minute becomes 1140 feet per minute. So a dramatically increase in the velocity in that flue pipe. I increase the velocity, the draft of the chimney or the available positive pressure available from the boiler may not be able to overcome the pressure drop in the chimney, and the boiler may not be operating properly. So not only is it important to know the firing rate, but it's also important to know what the expected burner setup is to make sure that I've accounted for the proper amount of excess air when it comes to sizing the chimney. Okay. Now, when we start to look at this, we've talked about the available draft side of things. We've also talked about the positive pressure, and we talked about how the burner and the excess air affect the mass flow rate through that vent. Okay. And from an aspect of velocity, one of the things we have to consider for the velocity and the pressure loss is the information about the chimney itself or the vent itself. What's the diameter and what's the length? Okay. The smaller the diameter for a given firing rate, the higher the velocity. The higher velocity, the higher the pressure drop per linear foot on the venting system. The more linear feet I have, the more pressure drop I have. So those are important pieces of information to know when we start to look at the overall sizing of the venting for the boiler. So for instance, if I say, from an aspect of this chimney, if I have a 30-foot long chimney and it is 8 inches in diameter, and I have a 1,000,000 BTU boiler at 9% CO2, that in that 30-foot long 8-inch chimney, there's going to be 0.08 inches of water column pressure drop. Okay, and that's just counting for this 30-foot long 8-inch diameter portion of it. If I increase my CO2, increase my excess air, and my CO2 changes from 9 down to 7, all of a sudden that 0.8 inches of water column pressure drop becomes 0.12 inches water column pressure drop, or an increase of about 50%. So when we start to look at translating the mass of combustion gases that are moving to sizing of the chimney, okay, it's important to know the length of it, and it's important to know the diameter of it, because when we start to look at these numbers here, these are what we're going to have to start looking at and comparing to the amount of draft available, the amount of positive, net positive pressure available at the flue collar of the boiler. Because if these numbers are too high, the boiler again will not be able to overcome the pressure drop, and we're going to run into issues with the boiler operating. Okay. Now, normally when we talk about venting, we don't talk about the length of the venting. We typically talk about equivalent length. And equivalent length is, I'm going to call it a shortcut in sizing, because when we start to look at sizing of the venting, it's not just the pressure drop through the straight run of pipe, but it's pressure drop through the fittings in that system as well. And the thing is, when I start to look at going through elbows, through T's, short T's, long T's, sweep elbows. As the combustion gases pass through those fittings, that generates turbulence, and the pressure drop with that turbulence is a lot more than the physical, it may be physically, the combustion gases are only moving 6 inches, 12 inches, 8 inches through that fitting. But due to the pressure drop, that pressure drop represents a significantly longer piece of straight run of pipe. So rather than having somebody go through a long calculation to account for every fitting or elbow in the system, every fitting is assigned a straight run equivalent length. Okay, and by using those equivalent lengths, it's much easier just to equate the maximum run that the boiler can operate with to a linear equivalent length run. So for instance, here is a table for long sweep elbows. So for instance, if I'm doing commercial boiler and I'm using long sweep elbows, a 45 represents about 5 equivalent feet. A 90-degree elbow represents about 10 equivalent feet. So when we start to look at doing an application, it's not where I have to calculate what the elbow represents. I simply use these tabular numbers and add them to the overall linear length to come up with the equivalent length and sizing. But this way here, it allows us to account for all of the fittings in the system and not just the straight run of pipe, because they all affect the pressure drop in the venting system. Okay. Now, the other thing that has to be considered, although it's not part of the venting system, is the combustion air if I'm doing sealed combustion. So if I'm doing a sealed combustion boiler, category 4, the boiler isn't just trying to overcome the pressure drop in the flue pipe, but it has to overcome the pressure drop in the combustion air duct, bringing the combustion air into the boiler as well. So we start to do calculations for designing of a venting system for a boiler that's doing sealed combustion. It's not just about getting the combustion gases out of the boiler, but it's also about getting the fresh air into the boiler as well. Essentially, the boiler has to be able to draw the combustion air in as well as force the flue products out. So that has to be part of the calculation as well. So we start to look at the factors in determining whether a venting system will work for a boiler. You know, these are really the things that we have to look at. We have to look at the firing rate of the boiler. We have to look at how much excess air is going into the combustion process. We have to look at the stack height because that affects the drafting of the chimney if it is vertical. And then if we're going vertical, we got to look at the flue gas temperature and the ambient temperature for that draft as well. We have to look at the combustion duct work. And then when it comes to category 4, we also have to know the available positive pressure that the boiler is generating, since that positive pressure is what's moving the combustion gases through the flue, and if it's sealed combustion, through the combustion air ductwork as well. Now, kind of at the halfway point, so let's take a look and see if we have any questions.
No questions at this time, Jody.
Yeah, I don't see any questions in there. Again, I always love the questions, so if any comes up as we go through, please ask the questions. So once we have all of that information, then it becomes, okay, how do I use that information to size the chimney, to size a venting system for a boiler? And the real answer is, it's really about how complicated or how simplistic you want to attach to the process, and which one of the references are you going to go to size your venting system. Okay, so we're going to start and we're going to work from probably the simple to, you know, get a little bit more complicated in it. So if I am doing category 1 appliances, I'm probably going to work off of a chart similar to this. This happens to be one of a series of charts from Nfpa 54. Okay, now with Nfpa 54 here, you don't need all of the information that was listed in the first half of this seminar. So here, Nfpa 54, here's a type B double wall gas vent, appliance type category 1. And for sizing, across the top here, I have vent diameters, which we talked about. And then here I have the height of the chimney. And then I simply have a lateral distance from the boiler to the chimney. So this becomes a very simplistic process where assumptions were made in the generation of this, but they are very conservative number. You know, somebody would not go wrong by sizing off of here for a category 1 appliance. So in here, I simply say, okay, you know, in most cases, I'm going to go in and say I have a 15-foot chimney. It's 5 feet lateral from the boiler to the chimney, and let's say it's going to be a natural. It's going to be an atmospheric boiler. What I'm going to say for my example, and let's say the boiler has an input of about 200,000 BTUs. So I'd simply come across looking at the various sizes. 3 inches too small, 4 inches too small. Same thing with 5. But when I get to 6, that combination of 6-inch chimney, 15 feet tall, 5 inches lateral from the boiler to the chimney, has a maximum input rating of 217,000. My 200,000 BTUs is less than the 217. So that becomes the chimney that goes for this boiler application. Very simple, very straightforward, easy to utilize, has been around for a period of time. Okay. Same thing goes if I'm doing oil. This happens to be out of the Appendix E, which are chimney liners in the back of Nfpa 31 for oil boiler burning equipment. Now, burning equipment, a little bit different. You know, a lot of these tables don't give you any BTU output. It's in nozzle size. So here, you know, that 0.5 to 0.1, for instance, right here, that's 0.5 gallons per hour to 1 gallon per hour. Consider a fuel oil in the vicinity of about 140,000 BTUs. So I would come in here with a height, a lateral, and then gives you a firing rate range for a liner. So for instance, the chimney is 25 feet tall. The lateral is 4 feet. A 4-inch liner has a maximum input of about 0.5 gallons per hour, or about 70,000 BTUs per hour. And don't forget, it's at 88% efficient. These are a series of charts based on the efficiency. So 88% efficient, which is about 12% CO2 and about a 300-degree Fahrenheit gross stack temperature. And again, these are a series of charts in the back of Nfpa 31. Anybody that's doing a replacement boiler should be pulling these charts out to verify the size of the liner for that boiler. The other thing with this, and you'll find most chimney liner manufacturers or venting manufacturers will have a chart very similar to this for sizing their venting system. Okay. So again, another simple methodology to go in there, look at put in a couple of pieces of information. And again, here it's about height, it's about lateral, it's about input, but with the oil, we want to know, was it 88% efficient or is it 85% efficient? So you do have to know the steady state efficiency and probably the gross stack temperature for that application. But again, a fairly straightforward methodology of sizing. Okay. Now, a lot of manufacturers will have various charts to help on the sizing side of things. This happens to be one of our older charts from back when we had what was called the Rondemat boiler. So this is a chimney sizing chart that's based on the output of the boiler, the height of the chimney, and then it's about the diameter. And things like ambient temperature, stack temperature, excess air, all of those are assumed. So this is a very conservative chart that's designed to work under a wide variety of applications. So for instance, if I was at 2 million BTUs and I had its chimney height of about 33 feet, here's 2 million BTUs. Here's 33 feet. It's somewhere between 14 to 6, it's somewhere in the middle, between 14 and 16 inches. So that's telling me for that application, I would use a 16-inch round chimney for that application. Again, straightforward, conservative. You know, you may find that if you went through and you did a longhand calculation, which we'll look at shortly, you know, that 16-inch may only be a 14-inch. It might only be a 12-inch, depending on the conditions. But this way here, if somebody's looking for a quick, easy way to size the venting and know that it's not going to be undersized, you know, it's a great route to go. But again, fine, manufacturers, a lot of them, tends to be one of our older ones, will have tables as such to do the sizing. Now, another methodology, and you'll find this is more prevalent when you start to get into the category 4, is the manufacturers will have venting options available, venting manuals that work their way through all of the options. And why every manufacturer will have a manual like this is because of the specifics of their boiler. So when I do one of these manuals, the manuals typically give me a lot of different options on venting, different venting systems. Because frankly, when you're doing category 4 and you're not depending on natural draft to move your combustion gases, you can take a lot of different routes to get the combustion gases outside of the building. And also with category 4, all of a sudden sealed combustion starts to come into the picture. So you also have options with the sealed combustion side. Now, the thing with the manuals, everything is always going to be boiler series specific. So it's not just going to be for a boiler manufacturer, but it's also going to be specific from product to product, because the conditions, specifically the positive pressure that's available at the breech of the boiler, may not be the same from boiler to boiler. So it's based on the positive pressure at the flue outlet. And rather than working off of pressure here, everything in the manuals typically are translated over into a maximum equivalent feet. So it's not about calculating pressure drops. It's all about not exceeding a set number of equivalent feet that's been assigned to that specific boiler with that specific size of venting. Okay. And in it, as I said, the vent and the combustion duct sizes are going to be specified by the manufacturer. And then from a venting standpoint, you have to stay within the required maximum equivalent length that's outlined in the manual. Now, the other thing that you'll find when you look at the numbers, although condensing boilers do generate some draft if they're vented vertically, because of the fact that we don't know how much of the vent is actually going vertical, you'll notice that there is no credit for draft when you start to look at these type of venting tables. It's always about being as conservative as possible to give us the best results. Okay. So when you start to look at it, the manufacturer will specify the venting system. Is it 2-pipe horizontal? Is it any various methodologies? And if there is something specific that should be known, so for instance, here you'll notice it says first elbow is not included in equivalent vent calculation. For this series of boiler, that's something that happens. But again, because it's boiler specific, you may not see that accommodation with other boilers from that same manufacturer. So I can do a 2-pipe system, and what you're going to see from the manufacturer is a chart something like this. So maximum equivalent length, horizontal or vertically vented, okay? And again, we don't make that the differentiation here. So if I do these size boilers, the intake air can be 3-inch, the exhaust 3-inch, and I have 198 equivalent feet of combustion air plus flue. Okay. Now, if I move up to a different size boiler, the intake can still stay at 3-inch. The flue, the exhaust is now up to 4-inch. I still have that 198 equivalent feet. The mass flow rate is up because of the higher firing rate, but by increasing the size of the exhaust, the vent of the boiler, still stayed within the maximum positive pressure that boiler will generate at the outlet of the boiler to move combustion air and to move flue products. So typically with most boiler manufacturers, you're going to see a chart like this. Okay, and you'll notice the numbers as far as changes. Here it is, I'm doing a single pipe vertical room dependent air. So I'm drawing combustion air out of the room, so there's no combustion air. But you'll notice from a number here, horizontal or vertical, I still have that 198 equivalent feet. And again, that's a characteristic of the the boiler's ability to generate positive pressure at the flue outlet of that boiler, okay? But from an aspect of sizing the venting system, it's straightforward prescriptive. It's real easy to work with because of the fact that there's really not a lot of calculations that do go into it, okay? Now, the calculation that does go into it, though, is you have to be able to measure the linear runs of piping, and then you have to equate the pressure drop or the equivalent for each one of the elbows. So from this, we're going to say we're doing 90s and 45s, and these are long sweep elbows. So the 90 equates to 5 equivalent feet. The 45 equates to 3 equivalent feet. Always check the manuals for your equivalents. If it is not a long elbow, if it's a short elbow, those numbers will change. So in order to find out if your venting system meets the requirement, it's all about measurements and counting. So I measure the length of the straight runs, 16 feet, 16 and a half feet here, 4 feet here, 7 and a half feet here, 9 feet here, half a foot here, 3 foot here, 12 feet here, 6 feet here. But then I account for the elbows. So it's 90 here. There's a 90 here. There's a 90 down here on the bottom. Excuse me, that 90 doesn't count. Waiting for this to come off of here. I have 2 45s. So I have 3 feet for the 45s. I have 5 feet for the 90s. I add it all up, and my total equivalent feet is 77.5, accounting for everything. And then I simply check the 77.5, make sure it was less than 198 maximum equivalent feet. If it's less than that, then this is a system that the boiler will work properly with the venting system. Okay, so out of the manuals, this is typically how a venting system would be sized. Okay. From an application standpoint, one of the bigger benefits of doing a category 4 is it is such a flexible system. Yeah. So you can do horizontal venting on the combustion air and flue, vertical venting, combustion air and flue. You can also do the hybrid system. Hybrid system, combustion air inside wall, flue vertical. And then also the room dependent air, horizontal and vertical. Thing with room dependent air, and I actually didn't throw any calculations in for that because of a time constraint. But remember, when you're doing room dependent air, you either have to have sufficient volume in the room to provide for makeup air, and it's going to be per Nfpa 54, it's all spelled in there, or I either need to have enough grills on the side of the room or louvers to allow the combustion air to freely flow into the room per Nfpa 54, or some sort of makeup air system to maintain the air as well. So we do room dependent. From a venting standpoint, it's very straightforward from the calculation, but with room dependent, make sure you have sufficient combustion air to support the combustion process. Okay. Now the other option that's available, and again, this is normally spelled out by the boiler manufacturers, is multiple boiler systems, multiple vent systems. The key with the multiple vent systems, particularly with category 4 appliances, is right here, okay? When I do a category 4 boiler and I am doing multiple boilers, I have to make sure that there's some sort of vent damper built into the system. Why vent damper? Is the boiler that's firing and the vent system is going to be positive pressure. I want to ensure that if this is an off-cycle boiler, the combustion gases do not back up through the boiler. And if it's room-dependent air, the combustion gases don't back up into the mechanical room or back themselves through that system. So by having that vent damper there, that ensures that I isolate the off-service boiler when I have one boiler firing. Okay. Not only is it about normal operation with the combustion gases backing through, but also think of it as from a maintenance standpoint. I want to be able to open up the combustion chamber of any one of the off-service boilers, and that maintenance would not be possible without that flue gas damper. Okay. And the manufacturers, normally what you see is something like you see here from a design, just as with the single boiler application, it's all about prescriptive. So for instance, if I have a specific boiler size, if I'm doing 2 boilers, the common vent is 14 inches. 3 boilers, common vent is 16 inches. 4 boilers, common vent is 18 inches. And with this number, the boiler can be assigned a max equivalent length. Again, keeping the design process simple. Now, on occasion, there may be situations where the situation calls for something that is outside of what the manufacturer has spelled out in the manuals for the venting system. And you'll find in most boiler manufacturers, you are going to see something like this little important note down here. And I'm actually going to read it. If the venting layout configuration described in these instructions are changed, it is the responsibility of the venting manufacturer to recalculate the vent diameter. Do not reduce venting diameters listed. So basically, this gives an out to exceed the maximum equivalent numbers. Yeah. So for instance, your system has, you're doing a category 4 appliance, and the system has, let's call it a lot of 90-degree elbows, which quickly eats up your maximum equivalent length. And the question becomes, I've exceeded my 198 equivalent feet. What can I do? Because I really want to use this boiler. Then it becomes, well, let's look at the sizing from a venting manufacturer. This happens to show part of the opening page from a program that Duravent runs, a member of the M&G group. And let's take a look and see how the vent system needs to be resized. So if I look at this, I'm actually going to look at a printout from a design. So here I need all of that information that we talked about on the front side. So this is going to be natural gas or equivalent. The input to the boiler is 570,000 BTUs. The burner is going to be set up at 8.7% CO2. The flue gas temperature is 165 degrees Fahrenheit. The ambient temperature is 60 degrees Fahrenheit. And we're using UL 1738 venting. Okay. There's a section here for the combustion air, if combustion air is being used. Here we're looking at linear runs, and now we're accounting for each individual fitting, 15-degree elbows, 30s, 45s, or 90s. So you have to have a fitting count here. Here's my vent chimney system data. If the chimney has a horizontal length, we put that in there. If there is a vertical, what's the vertical height of the chimney? Does it have, what kind of cap does it have? Is there any lateral tees? Any specifics about the termination? Here's my elbows. If it's not a category 4 appliance, does it have a barometric T in it? So that's in there as well. Okay. So all that information gets entered in there, and then it comes up with some information. Okay. So one of the things that you have to put in on the software, it doesn't size the chimney, you size the vent as you're filling in your data. So you can have an idea of where you need to be. Usually it's fairly easy because you know you need to upsize out of the manual. It needs to upsize out of the manual. So the solution is the chimney and the combustion air for this actually was going to be 8 inches in diameter. The pressure loss in that 8-inch diameter vent was at 0.03 inches. The chimney also generated 0.15 inches of water column because it was 60 feet tall. And overall, what the slide thing? Overall, the total pressure is going to be a minus 0.08 inches of water column. So this is where, when we start to look at sizing a chimney, we would take that total pressure and then go back and compare it to the maximum pressure available at the flue of the boiler and say, okay, is that number lower than the number generated then the pressure generated, and if it's lower, then the resizing will work with the boiler. But again, this is something normally done in association with the chimney manufacturer to be able to get that boiler to vent. Okay. In conditions where we're going outside of the manufacturer's manual for the venting system. Okay. Now, another methodology, and I do want to throw this out here because it often comes up into discussion in commercial boilers. A lot of times you may find that the vent system can't be sized larger and the boilers do not provide sufficient positive pressure to overcome it. So it becomes a matter of adding in a vent control system. So there's a lot of manufacturers out there for these vent control systems. And normally the vent control system comprises of some sort of terminal fan, terminal fan or draft inducer, you'll often hear it referred to as, some sort of controller, and then some sort of transducer measuring the pressure in the venting system. And basically the system is set in there, it's programmed to maintain a certain pressure near the boilers in the common for a multi-boiler system. And as that transducer sees a change in pressure, the fan changes speed as well to maintain it. So a lot of times when you see something, and I say small diameters, small diameters, long runs in comparison to what we would ideally like to see in their application. But again, it becomes another viable option for venting, and particularly I see it in larger commercial systems where there's a limitation in what the vent side can be. Okay. Now, the final thing we need to talk about is what's called the Jakowski effect. First time that they came up, they said this, I was like, well, what is that? And the simple description of the Jakowski effect is really the same mechanism by which water hammer occurs. But think of it the backside of water hammer. And what we're concerned with this Jakowski effect is if I have a boiler firing, particularly at high fire, and all of a sudden the boiler shuts down immediately, you have all this combustion gases in here moving at a velocity. And the concern is that since this is a category 4 positive pressure sealed system, if I shut off my source of combustion gases, no air being moved by the fan, no combustion happening at all of a sudden I generate a low pressure. And that low pressure, the concern is that low pressure could damage the flue piping itself. Okay. Now, a lot of times somebody says, well, what are you really talking about here? And I'd say in most cases, it's probably going to be a vertical vent. And let's kind of go back to some of the numbers that we're looking at. So if I had a stack height of 30 feet tall, my flue gas is 167 degrees and my ambient is at 30 degrees Fahrenheit. In addition to what the boiler is doing to move combustion gases, the chimney is also generating a negative 0.11 inches of water column of draft. So if this is a million BTU boiler and this is an 8-inch vent, and I'm at 9% CO2, that's 16.45 pounds per minute being produced, moving at a velocity of 910 feet per minute. So I have that mass moving at that velocity. I stop the process of producing it. All of a sudden, a void forms here and the pressure drops. And you can end up with something like you see here. So it might be hard depending on your monitor, but what you see here is this piece of venting near the outlet of the boiler has collapsed. And it's really because of this Jakowski effect. Now, the one thing about this is there isn't any predictor of when it can happen. We don't know it's in positive pressure exhaust vent system because they are sealed systems. They don't have a barometric or a draft hood or anything. And it's also probably more prevalent in the vertical applications because of the natural draft it causes. But the problem is if it happens, the flue gets damaged, it has to be repaired and replaced, and that heating system is offline. So with the Jakowski effect, because of that, one of the things that has to be considered in particularly in vertical venting systems with category 4 appliances, is adding in a vacuum release damper. What you basically have here is a spring-loaded damper, and if the pressure inside the vent drops, that spring-loaded damper opens up and allows air to come in onto the backside to prevent that low-pressure collapse happening in the vent. You know, can be added to a new project, could be adding to an existing one. Again, it becomes an option available when you start to look at venting systems if you're trying to ensure that your venting system is covered for all types of applications. So now let's see, it's just about 2 o'clock, so actually it's pretty good. So now we're back to our learning objectives. So we talked a lot about the factors involved in the venting system, you know, all the information that's needed, regardless of the methodology of sizing, and hopefully you see how it ties all together. We talked about equivalent lengths and why they're important for the venting, and it's really about most times the manufacturer's venting procedure, where we're working off an equivalent length rather than calculating a pressure drop. We talked about venting with category 1 and category 4 venting, and you know the real big difference between the two, the fact that the boiler is providing positive pressure to move the combustion gases. We talked about the sizing process, and then we talked about the Jakowski effect as well. So covered a lot of ground, I thought, in an hour, and it looks like we do have a couple of questions.
We do have a couple of questions, Jody. The first one is, do category 4 condensing boilers typically have multiple blower motor selections available depending on required system pressure drop? For example, 120/1 or 208/3?
Good question, Victor. What you're going to find is typically there is just one, there's just going to be an associated burner, because the blower is part of the burner for each one of the individual boilers. And then what happens is each boiler will have a maximum equivalent length associated with that burner assembly. So unfortunately, there's no way to go back and size it based on the pressure drop. And I believe part of that is the certification of the boiler. It just would be too hard to go through and work through all those iterations. So it's typically boiler, burner, which includes the blower as a package, and then a set venting length associated with that. And then what happens is if you're worried about lengths, now it's time to start taking a look at the diameter of it if you need some sort of variation, working with the venting manufacturer.
The next question is, which master spec section do you typically see used to specify category 4 condensing boiler vent? 235100 or 235123?
You know what? I'm gonna tell you, you've pretty much stumped me on that one there. I have to say, unfortunately, when I normally go into a specification, you know, I'm going through, you know, 235216 to look at the boiler, and since I'm not selling the venting, I typically don't go in there knowing that the venting is going to be specified by others. However, I will take a look, and when Miranda and I put together the answers to the questions, I'll take a look and see what I can find out for that. But unfortunately, I don't spend a lot in those sections of it. I'm a 235216 guy, and then also going to look at the controlled side of things.
All right.
And so first off, before I hand it off to Miranda, I want to thank you for spending an hour of your time with us. Hopefully you found it interesting, and oh, looks like we might have gotten one back again.
We did. We got one more. What are your recommendations vertical flue gas vent for category 4 condensing appliance? Min stack height above roof, manufacturer listed, exit cone and storm collector, no rain cap, etc.
All right. Again, great questions. A lot of that is spelled out in the manual. I've got minimums. Again, unfortunately, a lot of this is things that I tend to not memorize, since I always have the manuals at hand to take a look at it. Minimum stack height, you know, pretty much by code. Typically, we don't see a lot of exit cones. We used to back probably about 10 years ago, we did a lot of exit cones with condensing boilers. But now with the advent of polypropylene, we tend to see very, very few exit cones. In fact, this doesn't even show up on our drawings. So, we won't see the exit cones. The one that I will tell you is definitely no rain caps. Rain caps are always a prescription for issues. Because first off, with a category 4 appliance, we don't worry about rain going down the venting system. It is a stainless steel system that is, good down to probably a pH of about 3, maybe on the water. So we don't worry about corrosion of the venting system. And we're always already have a drain on the bottom of the vent, since it is a condensing boiler. So we're not concerned with the rainwater. If you put a rain cap on, the concern is in the middle of the winter time, that as the flue gas is leaving, you start to see an ice buildup on the cap, and it actually will start to close off and start to cause problems. So the answer on the ice cap is probably, it's going to be never, because you're going to run into problems, particularly if you're in a real cold weather climate. Exit cone, we don't see a lot of that. And on the stack height, I'll flush this out when we do the questions afterwards as well. And with that, I'm going to, as I said, thank you all for attending, and I'm going to hand it off to Miranda.
Great, thank you, Jody. Just a few reminders before we head out. Like I stated in the beginning, it has been recorded and will be on the video library within the next 2 weeks or so. If you wanted the PDH credit and you said that in your registration form, be sure to fill out the survey. And then once you fill out that survey, the certificates will be emailed out to you within 5 to 7 business days. The Academy email is on the screen, so if you think of any additional questions, feel free to email us and we will add it to that spreadsheet. And that does conclude our last PDH credit for the year. We do have 2 coming up on product-specific seminars tomorrow and Thursday, so be sure to check those out if those are interested. And if not, I hope you all have a wonderful holiday and Happy New Year.